just waiting for the live stream. Cool. I'm just going to start. Hey, everyone. Hey, everyone here in real life, everyone on the internet. Welcome to our DevOps Amsterdam meetup. I think it's the first one in quite a while, so this is awkward. We're seeing people in real life again. We're back to reality. Today we're hosted by Fiberplane. Elena's going to do a very short introduction about the company as soon as I'm done. Just want to remind you all that we do have a code of conduct that we expect you to follow. It's the same we use for our conferences. If you want to read it, you can scan this QR code. And the most important information I want to relay today is that we are, of course, doing the first DevOps Days in Eindhoven this year. So if anyone is passing by, here's a QR code so you can buy a ticket. And I'll leave it up here and let Elena do a quick presentation. 30% discount. Oh, don't say that. Yeah, so there's a 30% discount on this one. So if that's not enough incentive, I don't know what is. Anyway, just give a quick hand to Elena.
Hello. Hello, everyone. Welcome. We're very pleased to have Thomas here and also to have all of you here. So let me quickly share what we are doing, building at Fiberplane. I don't know if you've already had a look at our website, which might be a bit telling, but we'll have more to come. So we're building collaborative notebooks for site reliability and DevOps engineers, and we are enabling basically a better debugging workflow, better making sense of metrics and logs, and using the notebook form factor that is known in data science and combining them with pretty powerful, very powerful integrations and templates. And we will have a big release that's coming up in 2 weeks from now, on October 18th. We'll be releasing many CLI template-related stuff, provider-related stuff, and with the goal to make it even more useful. And we're pretty early on in our journey, so for us, feedback is super important. Working with people who can really accustom it to their own workflows and give us great feedback, that's very important for us. And so people who are enthusiastic about new technology, that's definitely, if you're one of them, that's for you. Yeah, check us out. Thank you.
I just noticed I can talk into this microphone. That's cool. All right, so just for your information, there's going to be 2 talks tonight, of course. The first one is going to be by no other than Ivan Merrill. Am I saying that correctly? I hope so. Very good. Then I just need to get the tech stuff to work because browsers and stuff is hard. No applause for that. I did it really, really fast. All right. So I'm just going to do a quick, or maybe not too quick, talk about the hypothesis-driven incident investigation. So he has a really catchy, cool title, Incident Response, Let's Do Science Instead. So really cool. Just a quick note, in between talks, we're going to do a break, of course. And just before the second talk starts, we're going to do a quick Kahoot where we're going to raffle a really awesome prize away. So someone is going to leave here tonight with a cool prize. Awesome. Well, give a big, warm round of applause for Ivan.
Important, and I'm not as tall as Thomas, so we're going to move that down there. Okay, so hello. I'm Ivan. I am Head of Solutions Engineering at Fiberplane. But more specifically for this talk, I've spent around 15 years in financial sector, deploying, monitoring, and observability tools, and helping people do incidents. And what we're going to go through today is a number of bad patterns that I've seen, quite a lot of scientific research that I've spent a long time with my head in research papers on, and hopefully a good idea on how you can do things better, and a hypothesis on how we can improve things. So firstly, I need to work out how to, there you go. So incident response can learn from safety engineering in other domains. In terms of safety and resilience in the tech industry, we are very new at it. This is still a new concept. If we consider the name site reliability engineering, that is still fairly new, more new than DevOps and everything. But compared to aviation and to medicine and the energy sector, they have a lot of history in this. And they have so much that I have spent the best part of a week and a half in theories and papers and stuff, and almost forgot to prepare my slides, which is why I'm probably not as prepared as I want to be today, but we'll see how it goes. So a couple of things to kind of lay the groundwork for the rest of this talk. One of the most important things that we need to understand is that complex systems involve humans. And when we talk about our systems, when we talk about a website or anything else like that, we are part of the system. It is not just the technology that we use, that we deploy, that anything else like that. And someone who unfortunately passed away recently, but Dr. Richard Cook was one of the founding leaders of this. He was an incredible person. He would go and perform kind of operations in the morning and then produce a theory on DevOps in the afternoon. And he was one of the biggest influences of John Allspaw, who is one of the kind of founding influences of DevOps. So he has this line of representation. And what we say is this is all the system. There is our technology that is below the line, that we don't interact with directly, that we can't necessarily know directly, but then we are above the line. And we are performing a number of actions all the time that are impacting that system, and therefore we are part of the system. Okay? He even goes so far as to say humans are the adaptive parts of the system. We are the bits that are introducing change to our system, right? And a nice way to think about this is, how long would your service run if it had no human involvement with it, right? Would it actually fall over after a period of time? That is something that we need to consider, and it's a nice way to think about how we are part of the system. Catastrophe is always around the corner. You're going to see Richard Cook's name come along this a few times here. This is Hurricane Sandy. She hit New York in 2012. I was part of a company that had a data center in New York. It got flooded. That was a catastrophe. That's a pretty extreme example of catastrophe. We were frantically getting servers, everything out of our data halls and everything else like that. But it's not always just a hurricane that is around the corner. It can be something as simple as a bad deploy. Another example that I have that, again, is a bit extreme is I used to work for a credit card company in the UK. In the UK, we have a financial advisor who appears on TV quite a lot. He's called Martin Lewis. If he goes on TV and he says, you should all go and look for a new credit card, we got a free load test, right? Because everyone would be on the aggregators, everyone would be looking for a new credit card. Our load jumped up, right? So Martin Lewis is always capable of appearing on TV. We cannot control that. It's his prerogative, right? But that catastrophe, or potential catastrophe for us, is always around the corner, right? So we're never that far away from failure. Change introduces new forms of failure. And again, you're getting used to this Richard Cook. He's a very useful person to know in this field. In DevOps, a large part of our role is to introduce change into services. If we look through these, we build, we test, we release, we deploy, we operate, we monitor. All these things are change. Be they entirely new systems, new features, bug fixes, even sometimes new content. There are so many things that we are doing that are introducing new change. And as we introduce change, we introduce new, weird, and wonderful forms of failure. What might have occurred last time might not occur this time because we might have resolved that previous failure, but that just means that if having resolved that, we're actually going to see a bigger failure this time, right? Because it's going to take more to go wrong because we're introducing more resilience to our system. So we need to think about that. Experienced troubleshooters rely more on case-based strategies. So when someone has a large amount of experience with troubleshooting a particular service or something, it's quite often called maybe instinct or the smell. They just seem to know what's going wrong with their system. They seem to be able to identify the correct signals quicker than others, right? And part of that, based on this study here by David Johansen and Wei Hung, says that people at the beginning, they rely on domain expertise. They rely on system expertise. But what they don't have is experience. And actually, once you've started to resolve similar incidents over and over again, what you're getting is you're getting experience with your system, and you then start reverting to case-based strategies, right? So rather than just creating a new theory on what's broken, off the cuff, you actually look back through your memory banks of what have we seen before? What is quite similar to this? Can we apply anything that we've learned before to this? Now, that's great for that one person. But part of the problem we find in incident resolution in terms of learning from incidents is that's often confined to quite a few people, right? And that transfer of knowledge is hard, right? And that's something that I'd like to look at in a little bit. So, I love a definition. So we're going to have a definition for incidents. If I'm going to spend the rest of the talk talking about them, we should all probably be on a level playing field of what they are. So John Allspore and, again, that person, Richard Cook, created this in a book that they released in 2018, I believe. Incidents are a set of activities bounded in time that are related to an undesirable system behavior. The key thing I want you to take away from this is it's not just something broke, right? This is not something that, just failed, and we'll cover that in a little bit, but this is actually undesirable behavior. If we think about technology, right, and we think about the way it works, I always love to think about this, that it's not just doing it because it woke up in a bad mood today, right? Computers aren't capable of doing that. It is undesirable in behavior, but it's probably been introduced by us, right? So we need to think about that, and we need to accept that it's highly unlikely that something just broke, and also incidents are very rarely one thing that just happened. They are a series of contributing factors that build up to create an incident. So now we've done that, let's have a look at what we're going to talk about a little bit more. So too often, in my experience, an incident starts, it is detected, quite often reasonably quickly. Sometimes it's an alert, in the worst case it's your users complaining, but then it takes too long to get to this incident resolution. And there are a number of patterns that I've seen over the years that I'd like to talk about first. So what we're going to go through now is a series of patterns that I've seen that are problematic. This is one of my favorite. I call it mean time to innocence, right? Something's gone wrong, your system is down, you know it's not right, but people are looking at their dashboard going, my dashboard is green, everything's fine. From my point of view, it's not our problem. Go and speak to someone else. And they'll probably tell you the same. Their dashboard is green too. And that obviously isn't fine. A similar thing is, we rely on runbooks. We have a runbook for every situation, and then we reach something that isn't defined by our runbook. What do we do? The problem that we see here is that people aren't building up their ability to troubleshoot. They're not building up their ability to reason about the state of their system. They are relying on a dashboard to tell them what's wrong. And I actually did talk last week at DevOps Day, at DevOps Day Berlin, on why the perfect dashboard doesn't exist. It's very unlikely that we're going to have some dashboard that's just always going to tell us what's wrong. No matter how many times marketing people would tell you that, it's just not the case, because we're introducing change all the time, right? So yeah, that is a very common pitfall that I see a lot of times. Guesswork. This is really dangerous. The best example I have is working at a company that had a major cyber attack, but they didn't realize that at the time. They just saw their first site go down. So they immediately switched across to the second site. This is, how old this is. This is before the cloud, right? We're talking kind of, well, not before it, but a decade ago. And as a result of switching across blindly, we brought down our second site as well. because we hadn't mitigated anything, we didn't know what we were doing, we just blindly took some action, right? Sometimes that works, but even if it does work, you haven't learnt anything, right? You've guessed, you've got lucky, and more often than not, you're not going to get lucky. This is really, really dangerous. Yeah, spending a long time on the wrong solution. I think most of us that have been involved in incidents for a while, or particularly in really large incidents, will realize that we spend a lot of time going down an avenue of investigation, and we think it's okay, we think we're really onto a winner here, only to discover, either by taking the action itself, or someone gives us a really obvious thing proving it's not, that that's not the case. And this one is probably the worst for eating up the time in our incident, right? This is the one that really causes us to waste loads of time and resource quite often time, right? Lots of people, lots of effort, lots of actions going on, and we're completely wrong, right? Happens more often than I think anyone wants to admit. Fear of failure. I was in a job once and I got told by my boss if I performed this change and it went wrong, I could be fired. That's not a great environment to work in. But then what that has is it has a knock-on effect of if I'm in an incident and I feel I need to take disruptive action, I maybe need to restart a server or kick some users off a server or do anything that is disruptive. I've got this fear of failure in my head, right? There isn't enough psychological safety for us to take the right action. And incidents are often highly stressful. And the bigger the incident, the more stress it is. The more coordination you have to do amongst people, the more effort you have to spend, thinking about this problem. So the fear of failure actually increases the more severe the incident, right? And that's a massive issue for us because, again, it's meaning that we're delaying action that we probably think is right. But we don't want to do that until we've exhausted every other avenue because otherwise, there's a high cost to failure. So those are things that I've seen during incidents, but now let's have a quick look at a couple that prevent us from learning from incidents. I really like this quote from Mark Twain, right? History doesn't repeat itself, but it often rhymes. And I think that's probably similar to incidents. If you have the same incident over and over and over and over again, then I'm sorry this talk isn't for you. You've got a bigger problem, you've got some engineering prioritization, probably you need to be resolving that thing, right? But what we do often see, and this is where that case-based strategy comes in, is that incidents aren't necessarily the same incident, but they're often similar enough to see patterns, to see things that we can reuse, right? And so in order for us to get better at these incidents, we need to be able to learn from these incidents. And in the terms of safety engineering, that is by far and away much more important than any single resolution to any incident, right? We're always going to have incidents. We can resolve them quickly, but actually the ability to learn over time is really critical. So, hindsight bias, and I think this is a wonderful quote, right? It seems easy to look back at an incident and determine what went wrong. The difficulty is in understanding what actually happened and how to learn from it. The number of postmortems or incident analyses that I've seen written up, it was a bad deployment, we redeployed some good code, it was fine, yeah? And it makes it seem really simple, yeah? Or, these errors started as soon as something else happened, right? It's a very simplistic way of looking at things, yeah? And oftentimes it leads us to follow some of the other patterns that I'll come through because we make it sound so simple that it seems incredulous that no one just thought of this straight away, right? The fact is, though, that we're all trying to achieve a common goal. We're not here going, I do actually know what's going wrong, but I'm just going to delay on it for a bit because, why not? No, we don't do that, right? We are always trying with our best intentions to fix this thing. So actually, if we just say afterwards, it was this thing, it was really obvious, don't know why we didn't get it first, that was the problem, we are removing our opportunity to learn. Hindsight makes it easy, hindsight is 20/20, right? We can always say that's perfect, but it never felt like that in the incident. Normative language. Now, this is one of the problems what we see often when we get to hindsight bias, right? This is where we apply some judgment, maybe of the people responding to the incident, right? Or we think that it is obvious when it wasn't. And we have no understanding of what was happening in the incident, but to us it seems obvious. Maybe we have more years with that company or more experience or anything else, and we look at it and just go, yeah, but why didn't you just do that, right? And sometimes I've seen it most often, I think, around deploys. Something deploys, an incident occurs, everyone afterwards just goes, it was really obvious that they didn't do this, they didn't test it right, they didn't do this right, I would have done that differently, right? We're applying a judgment there, right? And it might seem obvious to us, it might seem whatever, but it's not fair on those people, and also, you know, it leads to us thinking that human error is a common cause of incidents, right? And I'm not going to go into it because I tried to, and there's just too much, right? Human error is a bad cause of an incident. It should not be your fundamental cause. There is loads of research on this, but we can encourage a human error to be the cause if we use normative language. Mechanistic reasoning. This states that our system would be fine if it wasn't just for that one pesky component that broke, right? But that's often not the case, right? It's often not just one simple thing that broke. As I said, there are a number of reasons. There are contributing causes that lead up to the incident. If we get to this, it's kind of like encouraging us to look for the root cause, okay? Now, the root cause most often doesn't exist. Even if you did have what you thought was the root cause, you could probably go down to a further layer, right? I did a bad deploy, yeah, but then my deploy system allowed me to do that. Maybe my programmers aren't skilled enough. If you want to ask a question?
Is that related to chain of events?
Yeah. So I'm saying that if we rely on something as being the single root cause, we are not allowing for the chain of events. Normally, as if we come back to our kind of definition of incidents, it's a series of things that are happening in time causing an incident. But quite often in our post-incident analysis, we can blame one thing. It was that. It was this one thing that broke. And that's not the case. And therefore, we need to avoid it because it prevents us from learning. Because if we just say it's something as simple as that one thing broke, that's our incident, then again, we're losing a lot of opportunity to learn. So, science. I'm just going to have a quick sip of beer. I'm not going to read it out to you, but this is the definition of Wikipedia, the ever-accepted perfect version of the truth. One of the things that I like about it is it talks about building on knowledge, right? In testable explanations. We're not talking about the universe, we're talking about our system here, so we can just cross that out. But the other thing is that we can talk about this continual process, right? There is observations, questions, hypotheses, experiments, analysis, and conclusions. But then, based on our conclusions, we go again, right? Because this pursuit of knowledge in science, it's always there, right? It always exists. We're always looking for more. And there is a theory of falsifiability that was actually caused because of swans. So Karl Popper pointed out that having X amount of white swans never proves that their swans are all white, right? It proves that we've got a lot of white swans, yeah? And no matter how many positive reinforcements of the existence of white swans, the inductive reasoning that says, I only see white swans, therefore swans are only white, is broken. And actually, when kind of Western civilization started exploring Australasia, there we go, black swans. So we were never actually right, and no matter how many times we saw a white swan, we weren't ever saying all swans are white. That's stupid logic, right? So Karl Popper seeks to, I've got a quote here. So induction cannot yield certainty. Science progresses when a theory is shown to be wrong and a new theory is introduced which better explains the phenomena, right? So this is our consistent learning, our appetite to learn more, right? We're never actually right. Even if we get another piece of confirming evidence, we're just maybe more sure we're right, okay? Until such time as something points out we're all wrong. But then that's good evidence too. That's good information. We learn from that, and we can now come up with a better theory. So here is my hypothesis on incident response, okay? So a more scientific, hypothesis-driven approach to how humans perform and document incident investigations can improve reliability. I'm going to get really caught up between my F's and my TH's here, between theory of falsifiability and then scientific. It's becoming a problem. But anyway, right, so a more scientific hypothesis-driven approach. I will go through this in a bit, but my hypothesis, what I am trying to say to you, what I would like you to go and hopefully experiment with and try yourselves, is that if we follow a more scientific approach, we can actually achieve better reliability. And again, this isn't in the short term. This isn't that one incident that we just did what Ivan said and all of a sudden it was perfect. This is over a period of time, right? It's not going to happen quickly, unfortunately. I'm sorry. So, a hypothesis-driven approach. I'm not going to go through all this text, but essentially, we make our observation. We have a preliminary observation in an incident normally, which is our alert, right? Something is broken. We kind of know the question is we want to ask as well. What is this thing that is making our system broken? Right? Why is it showing this undesirable behavior? We can make some hypotheses on that, right? And we can then experiment. But in our experiment, we must be thinking about Karl Popper's theory of falsifiability. Said it right. So we must try and disprove what we see, right? We can make a theory, but we must be able to disprove it. We must try and disprove it. We must not just look for everything that says, I agree with your theory, and we'll come to that in a second, all right? If, in our analysis, we say, we did disprove it, our conclusion is, that was a bad hypothesis. We can make more observations because we've learned something now, right? What we thought was the problem isn't the problem. Let's make more observations with that knowledge. Let's go again. If we are unable to disprove it, then, again, we've learned something else. And we can either keep trying to find other methods of disproving it or get more specific in our hypothesis and try and disprove that. Or if we're reasonably comfortable, we can start going on to actually taking action. And we can actually go through the same cycle again where we say, what action should we take? We can make a hypothesis. We can try and disprove it. It's an ongoing process, the exact same as the scientific methods. A good hypothesis. It should be specific, right? Hopefully my hypothesis was specific, but I'm trying to say there is a clear outcome, right? I'm saying it will improve reliability over time, right? And it's clear because I say that we're using a scientific approach, we're introducing that into incidents, and it's going to improve reliability. I'm not just kind of saying, if we did some stuff, it'll all be great, okay? It should be based on the observations made. I spent 15 years in incidents with observability, with monitoring, deploying systems, helping teams run incidents, helping train teams to run incidents. This is based on my observations, okay? So we've got a quite narrow field of observations here, but it's also something that I've been speaking to plenty of other people in, spoken to lots of others. But yeah, it should be based on the observations made. If we see something happening over here, it's no good just pointing out something completely random, right? That kind of seems pretty straightforward. It should show cause and effect. I'll come into this in a little minute when I show you a good hypothesis. But yeah, there's no just pointing out, the cause, this happened, so do that. We want to show cause and effect. And the reason this is important is because it starts to build up, as you'll see, some kind of scientific language and approach and being able to explain to people context and why you've reached that situation. You haven't just plucked something out from thin air. You haven't just kind of said, I see that, so I'm just going to do this other thing. There is a reason to it. And that's really important when we start to want to learn over time. And finally, it must be possible to be disproven. Again, we're coming back to Karl Popper. If we can make a theory that we cannot disprove, that's kind of no good to us. Right? We can't actually do much with that, okay? So we need to make sure that we can disprove it. So, yeah. A good hypothesis. A possible explanation for high HTTP 408 error rate, which is timeouts, is that there is high database latency, creating a backlog of database requests, which are in turn filling our API database connection pool. We have an observation. We have cause and effect. We can disprove it by looking at the number of available connections in our API database connection pool. We can disprove it by comparing our current database latency to a previous time period when perhaps it was good. Notice I haven't just gone for one way to disprove this there, right? I'm not just kind of saying what is the lowest possible gate to kind of getting through this and saying it's all good. I'm really trying to kind of go into a little bit more. There's probably maybe some more ways that I could disprove this, but I didn't have the room on the page, right? So we'll leave it at that. But the point is, this is very specific. We have our observation. We have our cause and effect. We are being very, very concise with our language. Now, one of the things I'd like to point out is one of the big issues in incidents is communication and coordination, right? And in actual fact, there is a series of studies that show that the harder the incident, the bigger the incident, the more difficulty you have in coordinating it. Seems pretty straightforward when you think about it. There's more people involved, right? More people comes more communication, more coordination, less idea of who's doing what, right? And it actually takes more effort for us to think about this problem. We've got more background noise. It's a higher incident. Probably it's more stressful. So this is a concise way of explaining things. If I was to write this for everyone that is investigating this incident with me, they have a clear idea of what I'm thinking. They have a clear idea of why I'm thinking about it, right? And they have a clear idea of what I'm going to do to prove this, to try and disprove this more specifically, right? This is very simple for them to take forward. I agree there is some kind of technical language in this and with HTTP responses and things like that, but that's our domain, right? But I've given people a nice, simple, formalized way of doing this. If every single action that was taken in an incident was written out like this, maybe not every single one, right? I mean, maybe not every single incident, right? If it's a really small thing, okay, this might be a bit large overhead. But if we did this for all of our critical incidents, if we were this clear, this concise, yeah, then this is helping everyone involved in that incident, right? Yeah, kind of crucial, right? Why bother? Why bother listening to me? Well, there are a number of things here. The first one, and come back to our biggest waste of time, spending time investigating bad avenues of investigation. If we aim from the moment that we come up with a solution to disprove it, we are not wasting our time going around looking for things that confirm it. There are two kind of agreeing schools of logic here. One is confirmation bias. We look for something that agrees with what our theory is, yeah? That's a massive bias that we have to fight away in incidents, right? It does happen. The other one is theory-induced blindness. And what this says is, we've got our theory, we really like it. I don't want to hear about like that competing bit of evidence that says otherwise, right? I'm blind to it, yeah? If we immediately look to disprove, if we build up a culture within our organization of attempting to disprove things the first time, right? We are removing bad avenues of investigation straight away. I actually had one with a colleague today. We had something around some user issues. He thought maybe it was a login. We tried it. I was able to use the login that he was using to do something that he couldn't do. We disproved his theory very, very quickly, right? Had we taken another course of action, which is one thing we were considering, we would have actually wasted time. We would have got a false positive. We would have thought we were right. We weren't. We would have lost time investigating it. It sounds like a very simple thing. I think a lot of what I'm showing kind of sounds like quite obvious stuff, right? It probably sounds like a lot of what we're doing already, right? But this is the really, really big one. It removes those avenues of investigation. It allows for change as an incident changes. Incidents don't always stay the same. They degrade over time. They get worse, they get better. They change as we change the system, right? If we take some action, we do a deploy, we fail over to the secondary site, as in my previous example, right? We are introducing change to that event. If we are wedded to a particular hypothesis and we're not prepared to change, we're not prepared to be disproven, right? then we are never going to reach our solution, because the fact is that things do change. And as we know, change introduces new types of failure. Okay? So as our incidents change, we need to be able to adapt to that. We need to be able to come up with, new forms of hypothesis. And actually, something that might have not been able to disprove at the beginning might become able to disprove later on. And we need to think about that and be flexible with what we can do. We can formalize the language we use to explain decision-making. This is really important to me. This is kind of what I was going through earlier. If everyone starts to use a similar language, we can get to a more common understanding. When we talked about earlier, or when I talked, you listened hopefully, about knowledge being difficult to transfer, right? Part of that is because it's actually hard to explain what we know, right? If we can reach this point where an experienced person is able to show this was their hypothesis, this is why they thought about it, this is what they did to disprove it, they are providing a very formal way of showing they know what they know, and they're writing it down in a way that we can all understand it. That's really difficult to do. So if we can get more people doing that, sometimes they're good theories, sometimes they're bad theories, but they are all written in a way that makes sense to us. They are all written in a way that we can understand not just that was their theory, but why they had that theory, what observation they made. And that's a critical thing to learn from. It provides a level of safety. Again, right, if we have a clear understanding of what decisions people were using, the rationale behind them, right, and we are communicating them out to people in a very concise way. This isn't one person went off and did one random thing. This isn't, someone just had a stab at the dark and took a guess and it was bad, right? We are providing logic and reason to what we're doing. We are documenting that. We are communicating that, right? We are hopefully waiting at least a few minutes for other people to say, no, wait, I disagree with that hypothesis, right? And here's why I disagree with it. I've got this observation that can disprove it straight away, right? We are providing an ability to interact with other people. We are providing a way to document our decision-making that allows us to explain it, that allows us to, as I said, provide rationale to why we did what we did. And that makes it, hopefully, depending on your organization, but hopefully, makes it a lot safer to make those decisions, right? Because there is a kind of an artifact that shows why we did what we did. It avoids normative language. So again, when we start to build up our post-mortem, we didn't use it was very concise language, it was quite specific. We weren't using anything that said, Jeff said he thought he'd do this because, he just had a guess and I didn't think he was right, but, why not? We were very clear about what we were doing, why we were doing it. There was no subjectiveness to it, right? We are trying to build up logic, reason, right? And that's taking away the subjectivity. It's taking away they did that because they didn't know enough. They didn't do that because they chose to do that. This comes around from aviation, right? And the example given was that there was a particular disaster where the pilots actually chose to go down when they should have gone up, right? Now, in that particular situation, you're not going to look at it and go, well, it's easy to say they just made a mistake. That was wrong of them. But they didn't do that deliberately, right? There was a reason they took that decision. And it was down to the observations that they had, the signals that they were receiving, right? We're trying to avoid human error as this cause because it's quite often not the case. And in the heat of the incident, they did what they thought was best, right? So by allowing us to use a more formal language, a more objective language, we are trying to avoid that normative language which just isn't going to help us learn. And finally, hindsight bias is reduced as there is context. Okay, hopefully this point is kind of should be self-explanatory by now, but again, we are providing the context for every single decision we made, right? If we made a wrong decision, there is the reason why we made that decision. If we made a wrong decision, there is why we thought about it, what the observation was, right? We can prove that, right? So it's no good someone coming back to us saying, well, it was obvious that it was this. We can say, well, these are the reasons why we thought that, okay? We are trying, again, to remove that hindsight bias, to remove subjectiveness, to remove the judgment. We are providing a clear and concise formal language. So, creating a hypothesis. John Osborne wrote a thesis, and it was based on the process that people went through when they were in a major incident on an internet-facing website. The first heuristic that he came across was one that probably is pretty common to all of us, which is, what's changed, right? Creating a good hypothesis, the first hypothesis is pretty much always, in any incident, okay, who's made a change? Who's done a deploy? Who's done something? It often is the case, right? Not always, but it often is. So that is a really good starting point for our first hypothesis. If that doesn't work, the second heuristic was kind of throw the net out wide. Don't go too deep, but try and look at all these things, okay? And what he's trying to say there is, don't get lost in any specific avenue of investigation. Don't only focus on this, only focus on that. If you're certain it's not any change, you can disprove that. Throw it out wide. Come up with all kind of crazy things. If you've got several different components to your service, to your system, maybe let each team come up with their own hypothesis based on what they see, right? Try and come up with quite a few of these, no matter how random they might seem. Don't go too deep into anyone. Don't go too complicated in anyone. Keep them quite general, but throw the net out wide, okay? If you can, then you try and disprove them, as many of them as you can at once. But if you're stuck for that, then we can rely to Occam's razor. I couldn't find a good picture for this, so I just went with a razor. This is the principle that says the simplest solution is often, most often the right one, okay? So when we are going through our hypotheses, if we have spread it out wide because, we couldn't find any change or anything else like that, if we need an order to start going through them, then let's go with the simplest one first, all right? That's often the right one, but also, if we disprove it, again, it gives us more information. We can learn. It's not that simple solution, so what's the next simplest one? If we need to go through this for a while, then that's what we need to do. But each time we're documenting this formally, we're learning, we're providing an artifact of our incident that will help others learn in future, right? This is all good stuff. This is science, okay? So there you go. I think there's one last thing that I would like to leave you with. Back to Richard Cook, my favorite person to quote this talk. All practitioner acts are a gamble. When we're talking about incidents, we are talking about things that are unintended in the first place, right? They are an undesirable, things happening in our service. We didn't intend for this to happen. As a result, when we start to change things, we might have unintended consequences. We have to accept that, right? We are never going to reach the point where we can always know for certainty that our action will be right. Karl Popper has shown us that. We're only as right as we are until we get a bit of disproving evidence, right? And as a result, all actions are a gamble. We can never hide that. We just have to accept that, okay? So don't be too scared. Give it a go, right? And don't forget that if you are following this, you are teaching people after you, right? This is all learning. There is a huge amount of evidence to show that the more we learn from incidents, the more reliable we get, right? If you take an action and it doesn't work, you learned something. Move on from it. It's okay, because it was a gamble in the first place. So there you go. That is my talk, and that is my hypothesis. So I'm hoping that some of you are going to go out there now and start, even if you don't start using formal language or anything else like that, if you come to an incident, start thinking about disproving it, right? Start thinking about what you can do to say, how can we disprove this? Start thinking about a slightly more formal language to explain what you're thinking, right? If we all do that, if you start doing that repeatedly, then, I'd love to hear from you, because, as said, that's my hypothesis, but I need the experiment, which you can all help me with, to find out if it's true. And if it's not, then maybe I need to go away and create a better one, right? But thank you.
Well, thank you, Ivan. Perfectly on time, actually. That's quite impressive. So, if you have any questions, please do it now, or well, not here, but right now we have a break for like 15 minutes. So let's just say 5 minutes past 8. And if you want me to, I can come shout in the room again, or just remember the time, and I won't come shout at anyone. When you come back, we're gonna have a quick quiz. Like I said, someone's going home with a prize. Nice. And yeah, that's it. Thanks again to Ivan. Great talk. Thanks.
Nothing comes for free, and the hesitation got me so that I can't speak. Now the room is spinning. I got knocked right off my feet. No more conversation, just a possibility. I wish that I could stay a little longer. It's in your eyes, but should I even bother? It's somewhere lost forevermore. My demons come for me when they hear my voice.
Me when I fall, looks like I'm wrong. What's going on? Looks like I'm wrong. Clouds are closing in now. Must move along. Lightning striking everywhere now. Running fast, hear the cracking so loud. It's so loud. No. I say what's going on? What's going on? Okay. I thought
Indeed. 8-bit stuff. Hello, everyone. You might need to come closer to scan the QR code. I'm not sure. Has anyone here not done a Kahoot before? Does the word Kahoot mean nothing to you? Please raise your hand. Oh, we have experienced gamers here tonight. Very good. Okay, who's called not Thomas Craig? That's where. Who's the wise ass? Okay. Possibly. Okay. Is someone still trying to join? Because else I will get it underway. It'll get worse. Are you in? Everyone ready? All right. I will read out the questions because you're pretty far away. I will move the microphone around a bit. So here we go. Disregard the Eindhoven part. So, question number 1. What year did the first DevOps days take place? 2022, 2010, 2009, 1987. You can see the timer on the left. Stressful quiz music. Ah, 6 people got the answer correct. Very good job, not me. You're in the lead. So, which year did we serve the first DevOps at DevOps Days Amsterdam? 2014, 2015, 2016, 2017. This is for the diehard fans who's been to every event. I didn't block anything. So the correct answer, obviously, is 2015. Oh, the Wi-Fi password. Shall I try and type it? You got it wrong? You weren't there? Ah. 2015, yeah. Well, there was one that year as well. The point is there's one every year, but we started in 2015. Are we online, ready to go? Good. Then I will continue. Oh, maybe I should reveal what the price is already, so you know what you're playing for. Or should we keep it a surprise? Yeah, let's keep it a surprise. Hey, not me is still doing really well. Very good. Alexi's gaining on not me, though. Finish this sentence. Developers are incompetent, friends not food, slightly preferable to AI. They are friends, not food. Indeed. Very good. Just a show of hands. Who in here is a developer or categorizes himself as a developer? Very good. Not me is still in the lead. Very good job. So according to the book Accelerate, the Science of Lean Software and DevOps, which 4 metrics should you measure? Deployment frequency, lines of code, mean time between failure, change failure rate, that's the first one, total weight of team, beard length, pants, pizza slices per sprint, number of blameful postmortems, velocity, number of emails sent per stand-up, WTF BBQ, deployment frequency, lead time for changes, mean time to repair, change failure rate. Yeah, because it's a long question and long answers, so I gave this one extra time. The answer is also not very clear, so. I would agree. I'm not sure what science would say, though. Hey, almost everyone got it right. Very good. Not me is on fire. When are you finished on your DevOps journey? Once you've successfully implemented the safe agile framework, when PagerDuty wakes you up 12 times per night, that's very little. Never, it's about continuous improvement, or when my boss tells me it's done. Hey, good job, guys. The actual answer is actually green, but it should be yellow. Red would also have been, no, red would never have been okay. To use a microservice architecture, I must strive to have Java, Kubernetes, decoupled services, or very expensive consultants. Huh? Who said what? It's for anywhere. I would also have accepted this, and then you can hire me later. Organizations design systems that reflect their own communication structure. Whose law is this? Is it Moore's law, Newton's second law, Murphy's law, or Conway's law? It is Conway's law, indeed. We can go into why that's important another time. Ooh, we're getting close. Alexi, you have to kick some ass now. The CAMS acronym stands for Culture, Autonomy, Mastery, and Scrum. Culture, Automation, Measurement, and Sharing. Cats, ants, moths, and swordfish. Cheese, anchovies, mustard, and sugar. Oh, it was the blue one. Very good. You answered it faster than I could read it out. Yeah, Alexi, you're getting close. Where will DevOps Days Eindhoven take place this year? Yeah, it seems like an easy question. High-Tech Campus, Philips Stadium Eindhoven, Van der Valk, or P4 long parking at Eindhoven Airport? It's indeed at the High-Tech Campus in Eindhoven. Hey, EK, I don't know who you are, but you're on fire. Good job. Keep it up. 2 questions to go. True or false? Oh, this is the last one. I want to win a ticket for DevOps Days Eindhoven. True or false? Okay. Someone, well, that's fair enough, because this one awards double points, so whoever didn't want a ticket doesn't get one. Oh, and if you don't win, there's still a discount waiting for you. So let's see. In third place, with 7,049 points, is EK. Second place, Alexi. And the winner, not me. So congratulations, not me. Good job. You can get your ticket at this lovely gentleman here in front, if you really want it. If you don't want it, Oh, it was. I knew it was you, bastard. Awesome. Alexei, please get in hold of this gentleman here, and he can help you out. Oh yeah, you have. Yeah. Oh, good job, Alexei. All right, that's it. That means we can hand over. I can hand over the stage a bit to our next speaker. I just need to figure out how to get out of this again. This can go away. And then we go here. All right, the next speaker is none other than the best Brazilian in the world, some dude who works at AWS. He's going to be talking about different types of data architectures. Is that correct, Thiago?
Yes. Cool. Thanks.
A big hand, or whatever you say, big applause for this lovely little guy.
Let me put it down and say thank you to Thomas and congrats to Alexei for winning the ticket. The first DevOps was a great experience. At that time, I was organizing DevOps days for the first time. And I remember that was the time that we spent the most on it was on actually selecting the beer. So, and that became a tradition year after year. I think today is still that, right? I'm not part of the organizing team anymore, but is that the biggest effort, Thomas? Okay. Okay. Well, everyone, I want to thank you very much for joining today, especially because today is also AWS Community Day here in the Netherlands. And I'm impressed that people decided to watch me instead of Werner Vogel. So I might find that you probably didn't know about that, otherwise you wouldn't be here. But my goal today is to share how to build a modern data platform with you. And I hope that suits your need and help you evolve from wherever you are. And why that in a DevOps context? Well, we're all building something that requires data at some place, somewhere. And for the last years, I've seen more and more DevOps people going into the data part because they are complex systems distributed that need management and automation. It's not just setting up a SQL server somewhere, somehow, and doing some SQL queries that you can call a data platform. It can get complex. It can go into different ways. And I'd like to share that. Again, my name is Thiago. I lead the startup solutions architecture team on EMEA on AWS for the early stage startups. If you are a startup, for example, like Fiberplane, that I know somewhat well, especially after their funding last year, congrats on it. We help startups go through their journey, independent if they are building on AWS or not. We have a team of former founders, former CTOs, former people that help on funding, go-to-market, but of course my team is specifically on the solutions architecture part. And we don't take equity, okay? So no worries. The agenda for today is quite simple. We'll start by explaining what it means to become a data-driven place. We'll then spend some time into covering some core concepts, such as data lakes, data mesh, going through that, and you see how they all play a role in like building this modern data platform. I'll be using some concepts from AWS, and I will call out when you can replace them for, I don't know, Snowflake or a data warehousing or whatever tool do you want to use for it. I am not attached to the AWS products at all. I do what is best for the customer. And I'll leave you some recommendations on how you can best approach building this modern data platform on your organization. So let's get started by first defining what actually means becoming a data-driven business. Because first, I want to share with you the kind of quotes that I get from startups on a daily basis. Sometimes they tell me that they would like to share data more easily between their onboarding teams, especially now in a remote place and the majority of them being remote first, while still preserving some autonomy. It is that data sharing while still keeping control of data access, especially when I'm talking about, for example, fintech startups, healthcare, all of it, that security and governance appear to be the key point, and you need to know who is looking at what and when. And these customers also raise questions to us like, how can we treat data as a product? How do we move from a monolith first base data architecture that is usually, replication of your production database that you do SQL queries that is very, very slow to change to an approach that enable more agility. And all these points have led us to see data patterns and architectures that allow the startups to focus on innovation and moving on, and rather than just administering their data teams, because that's what we see in large enterprises. They start to become this massive drains of people just managing metadata or things like that just to make sure that everything is in place. In light of this kind of feedback, I think that there are three key attributes to consider when defining what it means to be a data-driven startup. Firstly, it's something that is built so that data can be treated as an asset and as a product and can be shared across your entire teams. Secondly, the data must be democratized, and especially when you look at, for example, talking about Fiberplane and other customers that are talking about incidents, you don't want to put tape around incidents before something is actually happening. You need to make sure that people can access freely with you logging who is accessing what and where in order to foster experimentation, in order to foster what it comes out of freedom. And finally, this data platform should have a lightweight governance that allows you that fine-grained access control, that fine-grained security. This evolution towards a data-driven company, business, startups, is because they're trying to solve specific business problems. And we find that the most common problems that we see are actually when you start to take step. Like you have your, like I said, SQL Server copy or your Postgres replicated one, and you want to move towards something else. You want to have some more data processing. You want to have real data analytics. You start to improve the customer experience through acting on this data. It's very, very common for us working with startups that they prove a point with an MVP or something, then they start to gather data and they want to improve their product or the behavior of the customer based on the data that they have. And that requires a different way of thinking that is not just adding a feature to your application. It's actually increasing how you build stuff. It's modifying how your data architecture is. And to start, let's cover some core concepts. The data lake, the data house, and the data mesh. And I must say, I am always unhappy with how data naming things go. From data warehousing to data is the new oil, to data electricity, to lake house, data warehouse, data mesh, and all of it. But let's keep on what the market is calling us, and let's call it out to what it is. So first, the data lake. How do we define a data lake? To me, this is best defined as a central repository. The central repository that allows you to store all your data at any scale. And you can store your data as is, or without having anything to structure it first, no schema on write or schema on read, you don't need to think about that. And then you can run different types of analytics on top of that. Anything from dashboards and visualizations or using a notebook-like thing that can access data on S3 to big data processing, real-time analytics, machine learning, in order to achieve your specific outcomes. On this example here, again, I'm sharing some specific Amazon products, but I would like to highlight that I put it underneath what they actually do. So Redshift is for warehousing. EMR is your way to run your data processing on top of things like Hadoop, Spark, or any kind of a similar tools. Athena for interactive insights, or like a Presto as a service. Kinesis Data Analytics for real-time analytics, and OpenSearch Service as your operational part of it. The important thing is we like to treat everything that can be stored in a data lake as something that can be stored in an object storage. If you're doing this on premise, we hope that you're using something like a Minio or something like that. If you're doing this in another place, try to utilize a cloud storage to store your data as is. And of course, there is the BI and the machine learning part that is crucial to it. And I have on purpose used this illustration here that is quite confusing at first to depict the evolution from data warehousing to data lake, and from data lake to lakehouse. A data warehouse is essentially a database with a different normalization that makes it optimized to analyze relational data coming from transactional systems and different lines of business that I'm going to call LOB from now on. The data structure and schema are usually defined in advance to optimize for how fast you want to run your queries, the kind of reports that you're building, and are typically used for, like I said, reporting, analysis. Data is cleaned, is enriched, you have sometimes a landing zone, it's transformed, so you connect as a single source of truth. A data lake, on the other hand, is different because we go now to a place where it stores relational data from different lines of business, but also non-relational data, and what people sometimes call unstructured data from mobile applications, click streams, events, IoT, devices, social media, and so on. And the structure of the data or the schema is not defined when it's captured. You can do transformations after it, but there is no schema definition when you are writing, or different from the data warehousing that we were talking before. Then you must be wondering, okay, then what is this lake house thing? Well, it is nothing more than a pattern. The lake house data domain is a pattern that allows you to connect your data lake, your data warehousing, where you store your data, and all other purpose-built services, like use the correct database and the correct service for what you want, for searching, for data processing, into a coherent one-piece data domain that is focusing on minimizing data movement. Because moving data from a place to the other sometimes is not expensive if you are inside one data center or one place, but still takes time, and we would like to minimize that. And as we're going to discuss today, you're going to see that this pattern is the foundation for the evolution that's now accumulated in what a lot of people call the data mesh. And since this is a somewhat architectural session, I will not be focusing on individual services or specific things, but I still wanted to give a quick snapshot of the purpose-built tools that we usually utilize in a lakehouse. And again, I put the definition underneath so everyone can take a look and remember what is it used for. But let's see the next step. Just to know, this purpose-built part is important because it gives you the flexibility. Everything here can be utilized. I don't want to use the word serverless because I don't want to discuss this further, but to me it's more serviceful than serverless of these things that we are building. Okay, so we have seen the evolution from data warehouse to data lake to lakehouse. So a lot of people were asking, what's next? And what's next for a lot of people in the discussions that we had these last years were the data mesh, the concept that it's another architectural pattern with two goals on intention. The first goal is to organize your data platform around one or more data domains, one or more specific points, like let's say you have a clickstream of your data that for you it is extremely important that is stored in a time series database, while you have some information that you are aggregating based on the usage of your customers that you are aggregating with a ETL process or something with Spark and storing in a Parquet file as a columnar storage on your object part. How do you make sure that these things are connected? So this is how we build this to make sure that you have and you can build data products on top of this. The second goal is to support the concept of data producers and consumers from all across your company, your startup, with a layer of lightweight governance. We know we cannot have a free-for-all cowboy zone when we're talking about data, so we still need some governance, but we need to minimize it. It may still feel a little bit unclear to some people here, so let me try to explain a little bit better with an example. To start with, let's see that our customers have built or can build a data lake or a lakehouse-based approach for a specific domain. And they can get all the benefits I mentioned before, but they, again, want to minimize data movement, use built-in tools, and reduce the cost, be reliable, be secure, all of that. All the things that we have in the well-architected framework that we put. However, when they need to evolve further by sharing this data between developers, between units, between geos, while keeping the autonomy. And that's when we say it's time to start considering a data mesh. When you go beyond, when you evolve, so if you're already in an enterprise or if you are a startup that reaches a point that you start to have a lot of units and a lot of people touching your data, it's a concept that is going to be quite interesting for you because you get more agility, a more lightweight approach to it, and some security entitlements together with the identity management that you get out of it. The most significant outcome that I've seen from startups that when get to this point that they need to share this is the conception of being able to build data products and add that to what they already have. And this diagram is just a little better visual representation on how multiple domains or teams or developers can move on from it. So the most interesting part of this approach is that individual lake houses from areas of your startup or for your business can be different from different lines of business. As an example, one line of business can have like one part of your startup can be really, really, really big in data processing. Like it's a specific data team that is doing a lot of Spark or Flink or something on it, and they are doing that on top of some S3 objects that are as raw as you can get, and they are putting that in another place, like data warehousing. Let's say you're using a cloud data warehouse like Snowflake. And let's say that you have a second line of business that is the reporting team. That is, on top of that, Snowflake building reports. Let's say you have a third part of it that is actually gathering the data from the IoT devices and actually storing that into S3 as fast as you can, and also building some real-time reporting on it. We stay true to this approach that we have always advocated for, and that is that use the best tool for the job. Instead of, as I've seen before, startups going for like for example, to Postgres and starting to add different add-ons to Postgres because they want to handle blobs in Postgres and time series in Postgres and blah, blah, blah. We usually tell, use the best tool for the job on it. So the teams can act more independently and communicate via what is important, that is APIs. So by now, I hope you can see that we have evolved from that humble data warehousing system that is mainly a SQL on steroids, a massive parallel processing with a specific normalization, to a domain-specific lakehouse, and how we can scale even further that to a data mesh where all these domains communicate amongst themselves only with APIs using specific built tools. Once again, please note that each node that we call from this data mesh is a purpose-built data domain, meaning It can be constituted of different products, of different services going into it, but there are API communications between all of this. It really, really is an important point to keep in mind, because the end result, and I want to further represent this data mesh from a single lake house to a minimum of 2 teams working together that are the consumer and a producer of your example. Sometimes this connection between these teams is quite common to be, for example, a Kafka cluster. And that is okay. We are aiming to achieve some specific business outcomes here, and how the teams communicate, again, to us, it is important that it minimizes the work of developers, and that means API and messaging systems between them. And we accelerate this independent delivery of business data, data domains or data teams, or even developers on itself, to be as independent as possible. And we try to increase the data security within domains so that the communication between them on this Kafka cluster, for example, can be as simple as possible with the granularity that you need. This will enable self-service. This will enable people to think about data as something that will be used to create any product for them, to discovery, to subscribe across an entire startup organization, and finally, enable continuously but lightweight audit and governance, because everything is logged. As always, I think I like to come with an example that is not a startup, but actually something big. Like the case of JPMorgan Chase is just one of many that we have worked on. I'm part of the, inside AWS, we have this thing called technical field committees, where people work across segments together, and I'm part of the analytics and the machine learning one. And by that, I have the privilege to work with things that are not startups. So at JPMorgan, they modernized their data platform by firstly evolving their monolith approach, that is an old school data warehousing system, to a very, very loosely coupled data architecture. And second, by focusing on this, they were able to think of data as products, creating across the enterprise very, 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 very separate products that had federated governance. And this strategy resulted in a lot of cost savings, a lot of licenses that didn't need to be renewed anymore, and promoted a lot of data reuse across the entire, as you can imagine, gigantic bank. Which are the key goals of a data mesh, is to avoid that data movement, like I was saying, and actually providing communication with messaging and with APIs between the data points. By now, I think I talk a lot about data product, so let's take a look at an example of what it is. The majority of the companies think of data as a platform and not as a product per se. And that's a fundamental change that I usually talk to startups. Even at the earlier stage when they say, we don't have data yet, we need to get customers. I'm like, okay, I know, but you have to think about, let's make sure that if you scale to 1 million customers or something, what is the data that you expect to generate and how you can create a product out of it? And if I was to define it, I would say that a data product is simply a broad, cohesive collection of data, analytics, machine learning capabilities, all aligned to a specific use case. For a lot of industries, for example, retail, travel, financial service, this is usually what they call the customer 360 view, which must incorporate data from multiple areas of it. The purchase, the payment, the demographics, the clickstream, everything that comes with it. And that needs to be together to create a clear picture of the customer. And without something like a data mesh, this independent communication that's very similar to what we call API, but with data, it would be very cumbersome to achieve this. So it's hard to be evolving and enriching, and whoever here has already worked in a data warehousing project in a big company must know that it takes 2, 3, 4, 5 years of something that doesn't achieve anything in the majority of the cases. So now let's dive deeper into the architectural patterns that allow us to create this concept of a data product and the data mesh. I must warn you, this is a big architecture, but I want to show with a good way. This is something that I get called a lot working for AWS. Like if I need to run a WordPress application and I follow the reference architecture, is just insanity. And that's one of the good parts of it. When we publish a reference architecture or something like this, it's the utmost case. But since everything is decoupled, it's up to you to build that step by step and to be getting the trade-offs of it. And I wanted to start with the pattern that is familiar to many and the most likely starting point of any data journey. If you look closer, you can see that this is a double click, kind of it, into a data domain of a specific business, which will effectively become a single node of that data mesh. So this entire thing here actually is one of these nodes. And here I'm considering like a big enterprise, how should they build this? But I just wanted to make sure, and relating to the previous talk, how complex systems are and all the moving parts around it. Okay. I already described this in a conceptual way, but now we will look at it in a more detail in a functional sense. Every data platform, and I'm looking at the image here so I don't have to keep switching so people in the stream can read me. Every data platform here starts with a set of existing data sources, which could be your object storage, your database, applications, your file stores, so on. From those sources, data is ingested into the lake, where we stick to the best practice of having usually 3 layers. Your raw layer, store data as is. Your trusted layer, where you do the basic cleaning and make sure that the validation of the data, because even though your developer that is publishing to Kafka says that they adhere to a specific Avro format, I don't trust it, so I need to validate that. And the refined data. And then we usually encrypt, govern, and control access of it. On this case, I'm encrypting using KMS. I'm controlling access and identity using IAM. And I'm utilizing lake formation. I'm logging using CloudWatch, and so on. We do all our ETL, at this case, using Spark. On this case, as serverless as possible, using Glue. And orchestrating data using something like Apache Airflow. You could switch that to a dbt and a Spark running on EMR. It's up to you. Finally, we have a serving layer, which can be anything from a cloud data warehouse, like Snowflake or Redshift, to a NoSQL database, like Mongo or Dynamo, or a notebook itself. That is purely depending on the use case and where you're sending this. Which is the endpoint of this node? Are you preparing this to send this as an API? Preparing this to send to an end user? Up to you. These serving layers, again, map to the appropriate consumer. And I also mentioned that these data domains are also the nodes that make up this data mesh, every part of that. And we often talk about these nodes, again, as producers and consumers. Teams or people are always producing data and or consuming data. Data producers usually share one or more data products and make them discoverable through a catalog. That central catalog that is so hard to build in companies that already exist enable like what we call the federated data governance. And you can maintain the security and compliance across all of these data domains without switching between individual accounts. Like that is the ultimate goal. And these data consumers can easily discover data and access these resources, preferably again via APIs. So let's zoom in into an example of a specific data producer. Let's say I'm building a data product, and again, a data product expose data through an API. We're looking at a single account, and you can see in the blue outline there that we have a data product account. In that account, you have something like an S3 bucket, an object store, and various services that are used by that data product team to produce their data. That specific team, that developer sometimes, makes their own choices of the data pipelines for ingestion into the object store. They own the actual buckets on this case, because I'm using S3, and they are responsible for the life cycle of the data. That includes everything from the SLA, the stewardship, the low-level security, the granularity. Everything is owned by that team on that node. When they're ready to share their data product, when they're ready to expose their API, they catalog this asset inside a central catalog. That's a service that, for example, Lake Formation offers. But if you want to go for an ISV or something that is not from AWS, for example, there is a former startup of ours called Colibra here in Belgium that actually builds that exactly to make your data product, your API, accessible by consumers and discoverable by other users inside that mesh. So you're exposing, publishing, and you can think of this as, again, a topic in Kafka that is being pushed out, that people can discover and consume on it. Producers then will use that central catalog to govern access to their data product and to throttle it even. Who can access? What? What is the password? How do I rotate? Usually through something like, again, Colibra, Lake Formation, and do a tag-based access control. But for now, let's see how this might look in practice. Here, I have a data product from, let's call, line of business 1. It can be a team, can be a developer, and a data product from line of business 2. If the line of business 1, if the line of business 1 creates a new table or a new data product, let's call it table A, they can grant permission to the second line of business, to this other developer. If we're using Lake Formation for this, for example, Lake Formation will in the end create an alias into their table in the line of business 2, and it will show up in their catalog. So it's kind of like a pointer in the cloud. Line of business 2, this other team, will then create a resource link within their catalog to point to the original table. That's exactly what we did with pointers in old school Linux. That's what we're doing in the cloud for data points. So the table A, so that the applications can reference it. Once that's done, that data product is shared with those users of that second line of business, of that second team. Please, just one thing that you don't have to recreate anything. There is no ETL. The pointer here automatically changes when there is an update to it. And that's one of the most magical things when I started to migrate from the Hadoop ecosystem towards the cloud and using something like Lake Formation, is that there is no data movement. I'm not copying anything and doing any ETL from anywhere. I'm just changing a resource link, an ARN. And all that data is accessed directly from the first team S3 bucket on that table via Lake Formation in this case. It is important to reiterate that all necessary data governance is still the responsibility of the data owner, not the consumer. Even though it's sitting in a central federated account usually, that data owner still owns the product, the database, the table, who accesses what and when. They own usually the encryption keys and the permissions that authorize access. On this example, via Lake Formation. They own the tagging process. They control what tags exist, where they are attached to which resources. And because everything is in a central account, auditors and all your security team and all of it will have a central location to validate everything within that entire data mesh. There is no need to go to hundreds of different accounts here to validate that everything is being shared properly. Similarly, the consumers, let's say consumer X and consumer Y, have one central catalog they can use to discover and access these data sets. So if you're using IAM or if you're using a SAML approach or any kind of access, you still have a central method to access your data. And again, I'll keep bashing on lake formation because it does some magical things behind the scenes, is that it takes care of vending this credential and records to your end users and allow those fine-grained entitlements down to the column and even to the row level. And since that metadata is in a central data catalog, you can search that metadata in one location. So this federated data governance is really, really a laser-focused solution that requires a lot of knowledge that I have used very, 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 very few when I startups, with the exceptions that get into the level of picnics and message boards and things like that. And now we take a look into the consumer. The consumers must first find the data, of course, and that's where the central catalog comes in again. Once they find that data set that they have a permission to see, they can request access to it. Once a producer grants the access to it, the owner of the data, the resource share is created, that pointer that I mentioned before, and the end users can access their data. And once the data is granted to the consuming account, that account can use any engine compatible with it. So if the data is on Dynamo, on Mongo, on an object storage, on a time series database, it's usually an API call away for whoever is using it by the end to process. Of course, if you want to do reliability and apply that letter queues and like all of it, you need to use a proper messaging system to gather that information and fan it out. But it's up to you. The data consumers then get to choose how to interface with that data. And it's ideally important to point out that you don't need to necessarily use SQL or JDBC connection or anything, because that's what you usually hear from these data tools, is like, we offer a JDBC connection, or you can query with SQL. On this case here, we're talking about APIs. It's up to you how do you want to build on it. And once our mesh expands to multiple consumers and producers, it starts to look something like this. You have a database in a specific team, in a line of business, another one in another line of business, and a third one. The first line of business is going to share table A on this case. The other line of business might share table B, and a third developer decides to share table C. At the granularity here, you can select specific permissions to consumer, while let's say we have 3 consumers. You can specify, I want just consumer X, Y, and Z to access, while the other team might say, I just want to give this to Z. Now what's important here is that the data, again, still resides in the producer's account on that specific lakehouse. There is no movement of data. The actual database and table will still reside in that central data account and are not moving. And permissions are granted account to account into consumer's account. When a data producer applies a tag on this case, correct permissions are propagated across all the tags that happen here. With this process of tag-based access control, you really can make the data sharing process a lot more natural. It's important to remember that all permissions will always go through, on this case, lake formation, but using other tools like Colibra would also go like this, regardless of where the computational parts are. This tag goes into the central account that the data does not get out of it, so your tags go into that point. Wait, it's not moving forward. Yes. So again, how data mesh patterns might look on AWS? Well, we first look at the peer-to-peer part and the centralized option. Here we have a central data lake with accounts on 3 buckets. Like I mentioned, raw, trusted, and defined, and refined. The first thing end user is going to do is register the data lake location. In our case, that means register these 3 S3 buckets that we're talking here. This tells the enable engines that this tool lake formation can use to access the data, rather than giving users direct IAM access. The second step they will take is to populate a data catalog. In this case, I put it here as an example, a glue crawler. The third step is to run these ETL jobs to enrich, refine, and move the data between these buckets, and also update the metadata table. The fourth step is publishing that data, making sure that they're going to create a database resource link from their account into the consumer account. And they're also going to grant a share from the data lake account to the consumer account, again, not via IAM users. Once a user has their permission in their IAM role that is linked to it, they can use any engine to process that data that is living in another account. They can decide to run a ECS container connected to it. They can decide to run their own Kubernetes on it if they have the identity verification with IAM. They can go into Athena, whatever they feel it's necessary. Oh, I forgot to pass on it. All the steps that I mentioned, that you first register the data location, then you populate the catalog, you transform, you create the database, and then you grant the consumer's IAM role into that specific table. And as the second to last step, you query the shared data set, and then we move on to another example with a central governance account. The biggest difference between the former account and this one is that here you register a data lake location. When you create that table, you also create something where the key here is that there is no data in the data lake account. And that's mind-blowing, that the catalog itself is empty. It's just a catalog of resource links. Essentially, all resources, all tables, all databases, they reside on the Federated governance account from all these teams, all this line of business. This pattern scales quite well with a tag-based access control, and it applies permission in a very, very automatic fashion. And to wrap it up, as I promised in the beginning, like to summarize some of the key points. Firstly, a data lake is the starting point of your modern data platform. You get to establish your foundation as infinitely scalable, cost-effective storage as you can, while the lakehouse is this pattern for building specific data teams and data domains and data products, while choosing the services you need. While the data mesh will build on top of that, this distributed architecture. So again, from a data lake, we go to the lakehouse, then we go into the data mesh. And if you want to go a little bit further, I will put some links and I will share this with you all, with some case studies, some learnings, and of course, you can scan this if you want to go for the skill builder. That is there is a specific course that we built for data mesh. So, thanks everyone, and if you have questions. No questions. Everyone was sleeping.
Any questions for Thiago? Else you can probably catch him before he runs away. So, just one big round of applause for Thiago again. Thank you. that also means I have to say thank you for tonight, and again, thank you to Fiberplane for hosting us. I think it was a great venue. I had some good beer, some good food as well. So, one last round of applause for Fiberplane, please. Don't forget to get your free ticket, Alexa. You did a good job. And the next meetup is the 3rd of November. It's on Meetup, so feel free to have a look. The talks aren't published yet, but they'll be there soon enough. Thanks, and thank you everyone who was there online. You may now consume beer.